Okay, hello everybody. We will be talking today about three things. We will be talking about vector, how to implement vector, and how to calculate its complexity. So we already talked about amortized time a little bit before, like the last lecture. On what have we finished with our... okay, yeah, we had amortized time on the stack, and we talked about how to perform, how to implement stack using 2Qs in amortized constant time. Today we will be talking how to implement the infinite array. How to implement an infinite array, and then we will be talking about heap, and finally we will be talking about BST if we will have time. BST is binary search tree. So we are coming already to very interesting stuff, I hope. So let's start. So we will start with the vector. The idea of the vector is simple. So suppose you want to implement a stack, and you want to add elements in the back and pop elements from the pop elements from the back. Let's think that we have only push right now, so we don't have pop, and we want to be sure that we will not use additional, a lot of additional memory. So how would the algorithm really work? So we start from array of size 1, then we add one element here, and we see that the next element that we are going to push is not ready to be here. So we copy array into array of 2 and put a new element. Then it is set. Okay, we should put another element here. That would be A1, A2. So what we are doing, we are creating an array of size 4, so we double the size and put element 3 there. Then we want to put element 4. We see that we have the length of this array's capacity, and the number of elements is size. So the capacity of the vector is the total memory that we have for the vector, and size is how many elements are really stored in the vector. So we add 4, and then we want to put number 5. Then we create another array of size 8 already, and copy everything here, and then continue. So each time when we are coming to the end of the array, we reallocate the new array 2 times bigger and put an elements into the new array. Okay, I claim that this of course you can remove elements from the back. Right now we are thinking about the simple that we never shrink it, but we will be trying to do that. The total capacity of the array is approximately not 2 times bigger than the maximum size of the stack. So for example, if you want to remove 5 and 4, we just remove it from here, and do not do anything with the array itself. Okay. Let's prove that the amortized time of this approach is of 1. So what's happening here? So simply you can calculate how many times you add an element. So you add 1 here, then you copy the array, you create a new array, you copy and add an element. Copy. This is copy. Then you copy and add an element. 2 elements. Copy. Then you have 4. Copy and until the next copying we have four inserts to get it to the next size. And as you can see, we can, like, it's simple to calculate that. Suppose we add 2 in the power of n elements. We will have 2 in the power of n once. So we have 2 in the power of n once. And how many do we have for the copying? We have 1 plus 2 plus 2 in the square plus 2 in the cubic plus etc. plus 2 in the power of n minus 1. So it is indeed 2 in the power of n minus 1. Like their sum of their powers of 2 can be telescoped to this value. Like that's, I think everybody understand that. If not, like ask the question. I'm pretty sure that you should know how to do that. Okay, so in total we have 2 in the power of n once and 2 in the power of n spent on the resizing of the array. So in total we have 2 in the power 2 in the power n plus 1. Like this is the total number of operations here, while the number of, like the total number of primitive operations, and 2 in the power of n is the size. So if it is the size, then the total number of elements is 2k, the total number of operations is 2k. Thus we could say that the amortized time is 2k divided by k, which is 2. So you could see that their amortized time is linear, because we never spent more than. Okay, that's kind of this algorithm works, like this proof of the algorithm does not typically work. This thing is that I'm quite hand-wavy trying to prove that their complexity is constant, amortized, but typically there are two approaches that are more formal than that. One is calling their coin budget, and one is using potential. So let us start with their coins. So what we will do, let us on each insertion of an element put 2 coins. Like suppose here, when we insert a3, we put coin at position n over 2 plus 1, and we put the coin at position 1 also. So kind of at each iteration we will put, like, kind of we spend at each position here 2 coins, which we will use later. So kind of we kind of say we spend time right now, but giving it to the future. That is what, like, kind of this. So you insert a 3 and put 2 coins. You put 1 coin here and 1 coin here. Then you have n over 2 plus 2. You put a coin here, and then you put a coin at 2 here. So when you add an element to position n over 2 plus e, then you put 2 coins at I and n over 2 plus I. Well, kind of at each operation we spend 3 coins. So we spend a coin to put an element there, and 2 coins for the future. So we kind of put a coin into the cell. Then, when we have to insert a new element and we have to resize an array, we simply spend the coins that are there by copying all the elements. So kind of, we know that we have from past, we have coins, and then we can use it. And you say, okay, we can use this coin, we can use this coin, we can use this coin, we can use this coin by copying the array there. So that means that each time we spend 3 coins, and that's it. That is enough for us to feed all the operations that are going to perform there. So this means that the complexity is amortized complexity is constant because each time we spend 3 coins. Is it clear? Do you have some question about coins? Let me check. Something. Okay, good. Okay, so this is about coins. So typically, that's the normal way to prove their amortized complexity by using coins. So you just, when you create an element, you just put some coins for the future and then you spend them together. So for example, there is an algorithm that, for example, insert so suppose that we have a very interesting data structure where you could insert an element, like in the tree, and then you decide to rebalance tree to be more, to have lesser height, smaller height. So we have a tree of some type, and it was like the number of elements were n. Then we perform n over 2 operations, insertions and deletions. So we perform n over 2 insertions and n over 2 insertions plus deletions. So like n over 2, the total number of operations, and then we can say, okay, let's rebuild the tree, rebuild from scratch. Build the tree. You can note that when you rebuild the tree, the whole size of the tree is at most 3n over 2. Then you spend here n over 2. So if you're using each operation, insert and deletion, you can put 3 coins for the future, and then you can use for the rebuild. So this is exactly the same as here. So we kind of put for the further rebuild some number of coins, and then we use it to rebuild their data structure. So that's the common way to prove their complexity of some data structure with amortized time. Then let's prove it using potential. We would say that each operation, the cost of operation I is equal the operation itself, how much it costs, plus fi minus fi minus 1. So what does it mean? Fi means the potential of the state of the data structure after insertion, and fi minus 1 is the potential of the data structure before the operation. That's pretty hard because you have to find the right potential for your data structure. So at first, let us say that we perform n operations and we request that fj is bigger than or equal to 0. Then, if you sum up all the operations with this potential, so it is sum of I plus fi minus fi minus 1. Oh yeah, and f0, for simplicity, f0 is 0. Then if you perform that, then the total at the end, you will have sum of operations, and everything here will be telescopically subtracted. So like, if you write this, so you have op1 plus f1 minus f0 plus op2 plus f2 minus f1 and etc. And you have like f1 that is right out by the next summand. So at the end you will get just plus Fn minus F0, which is bigger than sum of operation theta, sum of operation psi. And this is what we talked about last time. So for amortized for amortized time, we can say that their operation costs some another value, but the sum of these values is bigger than the total time spent on these operations together. So this is exactly we would suggest that each operation costs not op I, but op I plus their potentials itself. So the question is how to specify potentials in this data structure. So we have capacity C, and we have like their size S. So we want such a potential so that when you have the potential here, you will by adding an element, your operation. So your our operation when we copy it will cost C plus F I minus F I minus 1. So we have to find such a, so C is the capacity of the array. So here it was 4 and we are out of capacity. Then each operation, what's happening? What? Somebody took my Zoom conference out. Okay. Ah, no, everything's fine. So at the moment of copy, you have C plus their potentials of their states. While on when you don't copy, you have 1 plus Fi minus Fi minus 1. Because 1 is for putting one element there, and the rest is for the potentials. So we have to find some potentials so that during the change of the capacity 2 times, we will see that the previous potential is much less than the next potential. So it is less by this capacity. So suppose that we will take the potential as 2s minus c. Then what it would be at the moment of copying? At the moment of copying, we have can you tell me if we have the size 2 times minus capacity, so what will be in this case? What will be Fi and Fi minus 1? Could you tell me? If this is a potential, okay, so it's Si, sorry, let it be more consistent.
Well, Fi probably be 0, yes?
Fi will be 0, yes, because your Si is, it's not exactly 0, it is it is 2. It should be 2, because it will be, here it will be Ci is equal Ci over 2 plus 1. So then you double it, and subtract Ci, then you have this 2. Okay, good. What's with Fi minus 1?
Probably I minus 1.
Sorry?
Probably, so, well...
So we have Si minus 1 here and Ci minus 1 here. Yeah. What do we know from them? About
equal.
They're equal. Okay, great. Then the capacity is
Si minus 1.
Sorry?
Si minus 1 or Capacity minus 1.
Yeah, the size is.
Well,
So it is here Ci minus 1. Yeah. So it is. It is capacity I minus 1. So and then you can see you have Ci minus 1 here. You subtracted Ci minus 1 and you are left with 2. So this is equal to 2. So this is how the amortization with potential works. You just say there's some function for their you set some function for the state of your data structure. And for example, in this case, this is the right potential for the data structure, so that when you increment the size, like not increment, double the size, the previous potential will be much higher than the new potential. So let us add the, when we don't change anything, so we have 1 plus fi minus fi minus 1. So what will be here? So it is here S and C, and here is S minus 1C. Okay, because their capacity is the same, but their sizes are different. Like here the size is less on 1 than here.
Actually, the difference should be 2.
Yeah. Exactly, this difference should be 2, so it's 3. So to be more honest, so here should be 1, because like this is for copying, and this is to put an element. So it is 3 to be more precise. And you can see this is exactly the number of coins that we put during each operation. So this is not a coincidence that this is 3. So we previously put, when we put each coin, we put one operation and 2 coins. So this is kind of 3. And here we again spend 3 on an operation. So like this means that the amortization cost of this operation is constant. Okay, good. Any questions about that? Okay, if there is no question, let's move further. Then you will be trying to do this. Like the next thing you will be trying, I'm trying to get help from you, so you will help me. So okay, that was when we only increase the vector. So the size can only increase. But what if we want to maintain the following, that when you shrink, like when your size is very small, then the capacities also should be small. So we kind of should decrease sometimes the capacity. Okay, with the insertion, it is still the same. So we have array, which is full, and then you add an element and you copy everything to the half and like fill everything here. So this is capacity. This is capacity over 2 here. Here is capacity over 2, like. And that's it. So, and then you start to retrieving elements from the back. So you start to retrieve an element from the back. Where do you think we should do the resize? So we want to prove that we can maintain the capacity which is less than some constant x times size. I don't know exactly which is the constant x is, but but we want to understand when we should shrink. So obviously, when you have, when for example you want, like, if the size is less than C, or like the first idea that comes to mind, if when the size is less than capacity over 2, then shrink an array. Okay, that's the first idea that comes to mind. So like when C over 2 it become, then we copy it here. The only problem with this approach, like, do you understand why this approach will not work? Why it is too costly?
Well, first of all, our invariant wouldn't be true with such an approach.
Why? Here is the size C over 2, and here is the size equal to the capacity. So like we are fine. Like x is 2 in this case. Here their capacity equals to s. Here their capacity is to s.
Oh, okay. Yes.
Okay. So why do you think this will, like, this approach will be very, very time consuming?
Well, because if we're somewhere on the border, we will add and then delete the border element, and we will also always reallocate.
Yeah, exactly. So when you reduce it this size, you will get again to this situation, and then you add another element. You just should pay the total size of the array, which is not what we really want. So each time when you add an element and remove it from this near this border, as was said, we will have to increase and decrease size, which is very time consuming. So any ideas when we should shrink an array?
We could do 1 over square root or square of x. So in this case, it would be a quarter of the capacity.
Yeah. Okay. Yeah. So we will. So then finally, we have like this capacity, and here C over 2, and only after that we shrink the size 2 times. Okay. How can we prove that this indeed costs? Yeah, okay. As you can see here, here is C over 4, so x is 4. So at first we are good with the invariant, so like the real size of the array is not much smaller than capacity. But how to prove that we have everything good with their complexity? So previously, what we did like, let's put, like, every time when we add an element, we put a coin there. Okay, so we put a coin here, and then when we increase the size, we spent all the coins, and that is why we worked. So what we want really, we want to store some, like, kind of we want at this position to have coins at each cell. This is what we really want, to copy it to another small array. So any ideas on how to share coins this time? So now you have not only inserts, but you have deletes from that, so you kind of can pay additional coin during deletes.
I guess maybe like just add one more coin when we add an element. Would that
When we what?
When we add an element to the previous ones.
Okay. Unfortunately,
No.
if you you can have this situation, right? You can have C over 2 which is copied, and there are no more coins here, and I never insert any element there. I just remove it from the back.
Yeah. Okay.
Okay, so you don't have any
Well,
coins.
I thought that at the moment when we were adding elements, we would add not one coin to the, for example, to the ith element, but 2 coins. So after we copy, we're left with like 1.
2 coins. Okay, that's.
So then
I
copy
think
and
that's
spend 1
reasonable.
coin,
Yeah.
And then if we shrink and copy again, we can spend something.
Yeah, we can put 2 coins at each time, so we have 2 coins here. So we have, when we copy it, we have 1 coin here always. No, that will be a little bit complicated though. Because when you shrink and then, for example, you shrink the second time, you will lose the coins there. So no, like you cannot create 2 coins. This will not help. Yeah, but please note that you can add 1 more coin during not only insert operations, but also during delete operations. So kind of your operation will not only remove an element, but add a coin somewhere.
Oh, so then just similarly as when we edit an element, we edit a coin. So when we remove an element, we should also add a coin again.
Yeah, exactly. So when you remove, you put, like if you remove element from element I here, you take an element which is I minus C over 4, which is here, and put a coin here. Oh, sorry, there is no coin here. You just put it, like when you remove ith element, you just put a coin and at the first half of the array. Then when you come to here, you will have a coin everywhere, and then you could shrink. Okay, questions about that? Is it clear? How to prove it? Like each time we just spend 3 coins again. Not on deletion we cost like kind of 2 because we remove an element and put 1 coin, but previously we put 2 coins. So and you can see if we, for example, didn't shrink here, but we can go back to the right, starting grow to the right. Going here, we kind of create excessive coins, which we never will really use, but like that's you just kind of spend more than you have to, but finally you will spend only 3 coins in total per each operations, even creating an excessive amount of coins. Okay, so it is said that for this there is a potential if you are interested in. So there is 2s minus c when s is bigger than c over 2, or otherwise it is c over 2 minus s. If I'm not mistaken. So this is their potential, like if you want to prove it not with coins but using their potential function, you can do the same, like, and use this potential. Like there is nothing really here. So that is how you do the vector, and that is approximately how vector and vector in C++ works. Like it doesn't shrink back, so like this is the vector where we shrink back, and previously we talked about the vector that haven't shrink back, and the vector that haven't shrink back is the real vector behind in C++ and Java, and I think in Python also, when you add element, when you append element to the list.
Well, in Python I heard that the constant is different. Well, it's not like 2, but it's like something like 1.12 or something.
Yeah, the constant can be different. Like that's not a problem. Like, do you understand how to deal it with other constants?
Yeah.
That this is very similar. You just have to put more coins to the corresponding positions, and that's it. You just have to put more coins during an operation. Okay, good. So this is the vector. Now we will be talking about heap. So what is heap? Heap is the implementation of the following data structure. not data structure, following interface. So it is priority queue. So priority queue has two operations. Sorry, this marker is not good. It is extract min. So extract their smallest element from the set and add. And add new element. So why it is priority queue is that we always extract the minimum. So kind of we sort elements by priority and we withdraw the smallest element each time as we ask. This data structure is quite important because it appears, for example, in graph algorithms when talking about Dijkstra. We will be talking about that. But for now, like, we want to implement this. The main idea is that we will store the whole data structure as a binary tree. Binary tree is a tree that, like, it is rooted tree, so that each vertex has two children. And we will say that we will have complete binary search tree. This means that we are kind of adding elements one by one. So we just, at first we add element here, then we had, like, with the size 3, with the size 2 we have these two elements, and 3, then going from left to the right, and for example, the number of elements n is like looking like that. So like it is full tree at some point, and then all the rest elements are from left to the right, are joining to the tree. What we will maintain? We will maintain the following invariant so that each parent has smaller element than its children. Suppose we are holding this invariant. So can you tell me where lies the minimum?
So I think you drew it kind of weird, or I'm mistaken. It seems like they're both bigger, both children are bigger.
Yeah.
Both children are bigger. Ah, yeah, okay.
Yeah, exactly.
The root.
So it's in the root because it is bigger than each of its child, and we know that each of its child is smaller than everything in the subtree. So how we should add an element? So suppose we add an element here, element x. It can be seen that the parent of its element can be bigger than x. It is possible because we add x at the back and we don't know anything yet. So, and we want to maintain the balance here. So we will perform operation named sift up. So operation sift up will be doing the following. So we have element x and we compare it with the parent. If it is smaller than the parent, then we replace them. So like let it be p1, p2, p3. So we replace x with p1. And we know that already everything at the bottom, kind of in these trees, everything is satisfied. Then we take x and compare it with the parent again. If it is less, then we swap them, and you see that everything in this subtree where x are now correct, because p2 was less than everything in the subtree, and still p2 is less than everything in the subtree. So if x is already, since x was less than p2, then x is less than everything in this subtree. So the only thing that could happen is that x is still smaller than the parent. So by that, by going out, we can continually perform shift-up procedure. And that is how x can be moved up to the root, or we can stop if x suddenly, like for example here, if p3 is already less than x, then our heap is correct already. Okay, what to do with extract min? So this is how their add works. How to do with extract min? With extract min, it will be a little bit more complicated, a little bit. So we will take, let's take the latest element here, which is x. Like the latest, I mean, it is the nth element in the string, and we swap it with, like kind of not swap it. We just we withdraw this. So this is answer. This is answer, and we place x to the root. Then we perform an operation named shift down. So we take x and like something can be not correct here, right? Because you put some element x which was much bigger at the top, so something can happen that this x is bigger than children. Okay, who should be at the root? So it is A and B. So who should be in the root?
The one which is small.
Yeah, like since we know that A is smaller than everything in the left subtree, and B is smaller than everything in the right subtree, and X is somewhere we don't know. So either A or B should be in the root, be the minimal element. So we just take, for example, A and swap it with X. Then something probably is not correct right now in this subtree. Then you just compare it with the children and just swap it there, and like just moving down, down, down. So like that's why it's named shift up and shift down, because in shift up you just add an element and throw it up, while here you just make shift down, you just put element to the top and go down. So let us, so to be more clear, let us write the code for this data structure. So what is the perfect way to store? What is the perfect way to store this data structure? It should be an array. So it is 0, 1, 2, 3, 4, 5, and etc. And here. So they're consecutive because this is exactly how we build kind of this subtree. So like this are continuously growing, so from left to the right. So the question is, let us take an element I. Who will be the parent of ith? So if we take, if you have this array as their data, like as their identifiers in this tree, then we'll have here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, something like that. So this is how the tree, like this is how the tree looks, like this heap looks in an array. So we just write it from left to the right.
I over 2 probably.
But what with the 2? If you 2 divide by 2, you will get 1.
Well, for parents, okay.
You're almost right. You're almost right. So it is I minus 1 divided by 2, and rounded down. Okay. Who are the children? So who is left? I and right I.
So I plus 1.
Yeah, 2i plus 1. And the right?
Plus 2.
Yeah, 2i plus 2. So, okay, so now we already know how to get the parent and the children in the heap. So how to perform sift up? So, like, let us even do the following. Let us add element x. Then what we do, we say a n plus equals to x. So we kind of put an element at their nth position and increment the size. So then we say that the v is n minus 1, and because we incremented n already, so like it's n minus 1. You could write it like that, and then do n plus plus, nothing matter. And then we do while a of v minus 1 over 2 are bigger than a of v. Then we say swap a v minus 1 over 2 and a v, and v equals v minus 1 over 2. And of course, while v bigger than 1. And this. No, sorry, not 1, 0. So this means that while we are not at the root and we are less than our parent, we swap the values there and go to the parent. There is nothing non-trivial. So this is how AND works. So how works extract min? Extract min a little bit complicated because sift down is a little bit more complicated operation. So here is extract. So let me change the marker. Extract min. Okay, so we take answer as a0, and we say a0 equals to a n minus 1, and you say n minus minus. So like this is we take an answer which was in the root, we replace the root with the last element, and we reduce the size of the array. So then we say that v is equal to 0, and while 2v plus 1 less than n. The probably I'm mistaken somewhere here with equals. I'm 100% sure. And here we say if a of 2v plus 1 less than a 2v plus 2, then u should be equal to vn plus 1, else u equal to 2v plus 2. So here we just check who is the smallest of these children. Of course, here should be that the check that 2v plus 2 is less than n, because otherwise you will get out of bounds. So this if should be a little bit more complicated than I wrote it. So if 2v plus 2 is less than n and this, or this, then we should go like if 2v plus 2 is bigger than or equal than n, then 2v plus 1 is the only child, so it should be it. Otherwise, it is 2v plus 2. Okay, and then we say if A of V bigger than AU, then swap A of V with A of U and set V to U. Otherwise, break. So if the current value is bigger, then we should shift it down and go to the corresponding child U. Otherwise, we should break out of the loop because nothing will change later. Like our data structure is already in the good shape. Okay, questions about that? About heap? Okay, good. So let us teacher twitches offline. That's interesting. That's interesting. Check. No, it is indeed offline.
You put some element X.
Thank you for noticing. That's strange. Let me stop it. Let me start again. So it should be back, I think. Right? Because no. Oh yeah, it is back. So it should be back. Sorry for that. I didn't know. It is back. So let us continue then. So I have a question though. So first question: how to sort array using heap? And what will be the complexity? Like this sort is named heap sort. So you have an array A. And you want to sort it. So what? And you have a heap. What should you do?
Well, at first we should probably add the elements to the heap.
Mm-hmm. Okay. And then?
Well, then the first one would be the minimal element.
Mm-hmm.
And then we didn't calculate the complexity for the shift down, but maybe we could do it, or we could do something manually.
Okay, let's probably continue with this question. So we have add and extract min. What other complexities of them are? What is the complexity of extract min?
Well, I guess in the worst case, the x goes all the way down,
Mm-hmm.
so it would be logarithm n.
Yeah, okay.
So
So this one is of logarithm n, good. Is it clear that the size of this tree is logarithm n? And when you sift down, you can move only through log n levels. And it is by the complexity of logarithm n. And like for add, where we had sift up,
Probably the same.
yeah, exactly the same, because the height of the tree is logarithm n, and you just cannot move it faster. Okay, so the algorithm will be the following. So like you said, like let's add all the elements to the heap and do what then?
well, and then extract them one by one and put.
Yeah, extract them one by one and put them. Yeah, and that's it. It works in what time?
So it's 2 n log n.
Yeah, it is n log n because each operation costs logarithm n and like each n. So then I'm asking you an interesting question though. Given an array, build the heap on this array in linear time. So you are given just an elements and we are asking to build some heap, but in linear time. So if you put one element by one, it will be very slow, right? Because it will be n logarithm n in the worst case. And we want it a little bit more faster. Okay, any ideas? Do we have something in the chat? Okay, no. Okay, it's quite simple. So suppose we have a heap. We have here, here, so let us look on the latest layer of this tree. So each of these trees are already correct. Like if you consider only the trees consisting of one element, they will be correct. So then we look on the next level. How to make these trees correct? So we will
just
be
like, I guess, just take the minimum of the three and move it up a layer.
Yeah. So I would say in other words, if you will say in sift up and sift down notation, what should you do?
Shift up one element from the bottom layer.
No. Sift down. You should take this element and try to sift it down. We perform sift down here. So they are now correct and everything is fine. Then we consider the next level. This subtree is already fine. The only thing that is not the heap is the first element. So what should we do?
Sift down?
Yeah, we just have to sift down here. So that's it. Then if we calculate the complexity, so it will be 2n minus 1 plus 2 times, so like for each element at the bottom we spend 1, then on each element here to make it down we make 2 times 2 in the power n minus 2, then 3, 2 in the power n minus 3, like 4, 2 in the power n minus 4, and etc. Then n times, oh sorry, not 10, oh no, everything, yeah, n times 2 is 0, yeah, 2 in the power of 0. Where size is 2 in the power of n minus 1. Okay, if you don't believe, this thing is again the telescopic sequence, because if you calculate their 2 in the power of so you can replace it as 2 in the power of n minus 1 plus 2 in the power n minus 2 plus blah, blah, plus 1 plus 2 in the power minus 2 plus 1, then plus 2 in the power n minus 3 plus plus 1 and plus etc. So like each 2 in the power of I will be n minus I times calculated here. So kind of you build the first sum of powers 2, then the second sum of powers 2, and etc. We know that this one is 2 in the power of n minus 1. This one is 2 in the power minus 1 minus 1. This one is 2 in the power n minus 2 minus 1, and etc. So when you add them together, it is again the sum of powers 2, so it's kind of less than or equal than 2 in the power n plus 1. Which is 2 times size. So that is how we performed, how building a heap can be done in all of them. The question though if we can build a heap in O of n time, why the sorting works in n logarithm n time?
Well, because we need also to extract.
Yeah, exactly. Because you have to pay for extract, and extract works logarithm and so on. So there is nothing contradictory here. Yeah, we can build a heap in linear time, but we can't extract minimum out of that very fast. So this means that extract minimum takes n logarithm n time. Okay. Questions about heap? So this is priority queue, to be more precise. Like this is the simplest implementation of priority queue. It's not exactly heap, it's named binary heap because there are lots of different heaps like that maintains their kind of the same invariant that the tree looks like that. But it is not necessarily, like it is binary because it is represented as a binary tree. There are lots of different heaps like Fibonacci heaps or Metonic heaps, like there are lots of them, but they're complicated. They can, for example, extract minimum in constant time. For example, they can do that, but you cannot build them already faster. Okay. Okay, so let us talk about binary search trees. Let us start talking about that.
I'm sorry, but we have a lot again issue with Twitch.
Again?
Yeah.
Are you kidding? That's what's happening. Like, I'm thinking that that's a problem of Twitch rather than our problem. Or the problem of the OBS. Okay, so it's back again. So tell me when it will be lost again, okay? I will reconnect to the
Okay. So we can start.
Yeah, just say it and like I will be like anyway I will upload the recording, so like everything should be of good quality then. So sorry for the inconvenience with Twitch. So okay, binary search tree. What is binary search tree? Binary search tree is a data structure that looks like a tree and again has no more than two children. So we have left child and right child. And each element, each node has an element there. And we will maintain the invariant that all the elements on the left are less, like everything in this subtree are less than the element, the node, and everything on the right is bigger than the element in the node. So we will be maintaining this invariant kind in our data structures. The question though, do you need an example of the tree? Well, we could start. So typically binary search tree supports, so it implements the set interface. So, and set interface has 3 operations. It has contains, x, insert, x, and remove x. So let us start from the first one. So suppose you are given a binary search tree, and you want to find element x. How would you work with that? So like,
well, we look at our root. If it equals, then we return. If it doesn't, then we search. Then we look if it's bigger or less than our root. If it's bigger, then we look at the right subtree. If it's less, then we look at the
Exactly. So we compare x with the root, and if it is less, then it should be in the left subtree. If it is right, then it should be in the right subtree. And then you just go in recursively to their children. So there, it's not it. So there exist 3 different versions of binary search trees. So there exists internal, external, and partial external. So what does it mean internal? Internal means that all their elements are keys. All the nodes contains keys. Okay. External means that it is a binary search tree still, but the keys are only in the leaves. So everything here is the routing information and that's all. Real keys are only at the bottom. And partial external, this means that some, like this is the binary search tree, but some of the elements are kind of removed. So they are there, but their key itself is not there. So there are like 2 types of nodes there. There are routing nodes and there are key nodes. And they're not necessarily in the leaves, but somewhere in between. We will not care about that. We will be typically talking about internal and external, and that's it. To be more precise, we will be talking almost about internal, because in the internal, you can see that the insertion and deletion will be kind of faster than in external, because if the size is logarithm, if the height of the tree is logarithm, and both in internal and external, internal is faster because all the nodes are containing keys, while there are some of the nodes only with routing information. Okay. The first question. Okay. If we want to insert an element in internal, what we're going to do? Like, we're not talking about right now about balanced trees. We will be talking about balanced trees later. So what is balanced tree? Balanced tree means typically that the height of the tree is logarithm n, so that all operations will work in logarithm n. Right now the contains is working for the height of the tree, or for the height of the x, where the x is lying in. So how to do an insert in internal tree?
One version would be to go from the root and compare with the inserted element and just go until we find a place for it.
Yeah. Yeah, so we go from top to the, like, we are trying to search for x, and at some point we get to the position where no children there. So this is exactly the place where we should insert our x. So you just create a new node and insert it here. Okay, this is how insert works in internal. How in external insert should work? It's a little bit more complicated, but not so much.
Well, maybe we should go all the way from the root, but there would be leaves, and we should resuspend those leaves with a new rule.
Yeah, so we're coming here and we see, okay, I don't know, here we have to go to the right or to the left. You have to create x, but we have to maintain the invariant of the external tree that no inner nodes maintain the keys. Okay, so for that we just create a new kind of rectangle vertex with the routing information there, where we have on the right x and on the left the other node that was there. Okay, good. Then the question is, like, let's start from the external because it is much simpler, how to remove an element.
Here we will just remove an element and replace the rule with a circular vertex.
Yeah, so we find x here, and we just unlink this guy and link this guy back. That's no problems, that's easy. What happens in internal? It is much more complicated, unfortunately. So with external, that's it. We just like do something with the leaves and that's it. Suppose in internal we have to remove, sometimes we have to remove a node out of the middle of the tree. Yeah, so for example, here is x and we have to remove it. So what should we do? What should we do to remove x from the tree? Because it's like the tree can be very large out of that. X can be even the root. So what should we do?
I guess we could take the element which is bigger, the left one, and set it as a root.
Which is bigger? What do you mean by which is bigger?
Well, so for example, we need to remove x, yes?
Okay.
So then, wait, let me think of it.
Yeah, that's not very trivial.
Yeah.
Like you have to find the proper value to replace with. But like their idea is already correct that you have to replace with something which is bigger. The question is how to find it and what to find it.
Well, maybe we should look at the left node and then go through the right branch until we find an element which is...
Okay, that's also correct. So you just go to the left once and you like on what we could replace x. We could replace x with an element which is either the next with the value, with the next value or with the previous value. So how to do that? Like to find the next value, you just go to the right one time and go always to the left while you do not find the node. Like, for example, here we go to the right, then go to the left, then there is nothing to the left. So this guy is the next. There you only once go right and every time then go to the left. Because if you go to the right, they're already bigger than this one. Then you should stop here. Here is the same. You go to the left. How to get the previous, right? You go to the left, and then you try to go to the right as much as you could. For example, here there is nothing on the right. Thus, this is the previous node. Okay. So what you should do, you just have to unlink this node. Luckily, you can prove that this node has only one child. That's pretty simple, because if it has, for example, here left child, then this node will be the next. So it doesn't have. And to do that, we just take this y, you replace x with y here, and remove this node from here. So, and your tree is still correct, because everything were here, everything were less than this node, and if we link it, everything is still less than this node. So thus, okay, that's with insertions and removal. The operations of next and pref I will leave for the next time, and for today we are done, I think. Okay, thank you very much for coming. See you next time.